Well, thank you very much for the introduction, Jamie. As you said, my name is Cameron Thomson, and I work for ARUP, and I'll give you a little bit more background on the firm in a second. But I was going to talk to you this evening about some of the work that we do in regard to developing big projects, namely sort of campus scale projects. And I've actually been working with the University of Toronto. We've kind of finished our work now, but we spent about a year and a bit working with the University of Toronto, thinking about their infrastructure or your infrastructure and how to prepare it to be low carbon in the future, and then all the other challenges along the way. So that was the main thrust of what I was going to talk about this evening. I was going to mention another couple of projects along the way as well. So hopefully I've pitched this right, and it's got a little bit of technical information, but it's also a lot about strategy, and just to generally help people understand how people like our firms and other firms think about these kind of problems to help society. So some of it might be a bit 101 for you, but hopefully not. And as Jamie said, please feel free to ask questions. We've got, I think, 45 minutes left. No, we've got an hour and 15 left, but I don't want to be talking the whole time. It'd be great to hear from you guys, any questions you have, and get a conversation going. So without that, I shall get going. So I'm going to tell you a little bit about our firm very briefly, just to give you some context, and then talk about the context of the work that we do, our approach, and then some case studies, as I mentioned, basically focusing on the University of Toronto work that we did, and then some future considerations, and then open it up for questions. But as a questions along the way would be great. So what I hope that you guys would get from this, these are some learning, just basically understanding what the options are and the challenges are for converting an urban campus to a low carbon solution, understanding the impact of the grid and the interaction that we have with the grid and in terms of our low carbon choices, and what does an implementation plan look for projects of this scale. So a little bit about our firm, just to give you some context. We are a design consultancy, and we work across the whole urban development theme, looking at individual buildings, city scale, and then everything else in between. So my team, for example, we do green building, net zero buildings, etc. A lot of planning work like the stuff I'm going to talk to you about, but we also work with cities, corporations to develop their strategies. We're about 14,000 people globally. There's about 10,000 projects at any given point, and we've got offices all over the world. And in North America, we have about 1,300 employees across 12 offices. And I'm based in New York, but I did spend a lot of my time going up and down to Toronto pre-COVID, almost on a sort of weekly basis, to work on projects up there. But I've also worked all across Canada. One of the things that our firm has done over the recent years is align ourselves with the US Sustainable Development Goals. It's a theme that a lot of countries are doing, cities are doing, and corporations as we deal with the climate crisis and a whole bunch of other related challenges to that. And these are a set of goals which I'm sure you're familiar with, that basically give something of a roadmap about how the planet we would like it to look by 2030. And these are various commitments that you make, and then you sign up and develop an action plan to do that. And that's been really interesting for us as a firm, because it means we think about the kind of work that we do with much more scrutiny, and the kind of projects we want to get involved in. You know, are they actually moving the needle in terms of dealing with the climate crisis, etc. These are just the kind of projects we get involved in. Some of the bigger ones, certainly. So on the top left-hand corner, Waterfront Toronto, as Jamie mentioned, working on this for the last 10 years in various different capacities, assessing future developments, whether they actually meet their guidelines, helping them develop guidelines. Was recently involved on the Waterfront Toronto side with the new developer that was potentially going to go there in terms of scrutinizing some of their work. That we've done. This is a Champlain bridge in Quebec, a huge bridge that we developed over a number of years. And then we do other projects all over the world. This is the Apple campus in Cupertino that we developed the design for this building. This is all solar panels all the way around. It's a net zero building, although that's what happens when you have a giant checkbook. You can just throw as much money at it as you want. And then one of the seminal projects which started our firm really was the Sydney Opera House in Sydney many years ago, and we developed this was a small design in many ways back then, and this is the beginning of computer engineering. And we used computer engineering right at its inception to be able to achieve these designs. Seems to have frozen. So now I'm going to switch gears, talk a little bit about the drivers. I'm sure if you've signed up for this course, then you're well aware of these drivers. Just as a refresher, so we are in a climate crisis. It's manifesting in all kinds of ways with extreme heat, which existing infrastructure based on old design guidelines is suffering. We have things like blackouts. This was Superstorm Sandy back in 2012, where this is Manhattan, near where I live. This had a massive blackout. The bit that's still lit there was because they actually had power resilient infrastructure in place, so they were able to keep the lights on. Sea level rises, causing all kinds of challenges, and nations literally getting wiped out. And then, as I say, it's affecting all kinds of infrastructure with extreme events as well. The governments of the world have taken notice of this. We've made a climate pledge. Hopefully, the country that I'm in now is going to sign back up to this pledge. But essentially, we're trying to limit the planet warming up by less than 1.5 degrees. To do that, we have to do some pretty aggressive things. We have to reduce our carbon emissions from 2010 levels by 45% to have any hope of achieving this, which is very ambitious. But hopefully we can do it. I mean, honestly, we have the science to do it. We have the know-how to do it. It's just a matter of making the economics work and the politics work around it. So buildings have a huge part to play in this. This is a very generic number, but approximately 40% of the greenhouse gas emissions come from buildings. That varies from country to country. It varies from city to city, etc., depending on density. But that's a kind of rough rule of thumb, and you can see where the rest of it comes from in terms of transportation, etc. And we're also, apart from pledges being made at a global level, we're actually starting to see very aggressive action being made at certain cities. This is in New York, sorry for the New York-centric kind of presentation. But New York has done something very bold about a year ago, last April, on Earth Day. Basically came up with a new, it's not a carbon tax, it's been called a carbon tax, it's really carbon fine. But basically, if your building is over 25,000 square feet, which is a pretty big building, you have to meet certain emission targets. If you do not meet those targets starting in 2025, you're going to be fined $268 per ton of emissions you are over that limit. So if you're this guy, the Empire State Building, which has actually had a massive retrofit, so it's in relatively good shape, but if that wasn't in good shape, you'd be looking at millions of dollars of fines year on year. So aggressive things are starting to happen, or interesting things are starting to happen. Some of the levers are getting put in place to actually move the needle on climate change. And then another sort of interesting development that's happened that affects a lot of the work that we do is that the private sector is really waking up to this challenge as well. So this guy, you can see in the image here, is called Larry Fink. He's the CEO of BlackRock, which is, I think it's the single, if not one of the largest investment firms in the world. Every year, this guy writes a letter to all the Fortune 500 companies with some kind of guidance on or something they should be doing to improve their performance. And he wrote, and they're very influential, these letters. And this year he wrote a letter basically saying, if you're not taking climate change seriously, within your organization, then we're no longer going to invest in you. So that has meant a whole lot of corporations throughout the world have rapidly been developing climate goals and are now developing climate action plans to go along with those goals. Some of them are very robust. Some of them are quite meaningless, and there's everything else in between. So it's a very interesting time, but stuff is starting to happen. But the long and short of it, what it means in terms of meeting some of those targets, the 1.5 or even more aggressive than that degree reduction, is we need to have a transformational change across our whole built environment, from everything from our transportation, our infrastructure, but our buildings. And that's some of the work that I'm going to talk to you about today. So we have developed an approach for doing this kind of work. So as I mentioned, the world is urbanizing rapidly, and it's predicted that within 50 years, I think our urbanization centers are going to more than double. So people are looking for space. They're developing denser and denser cities, and then you're seeing all kinds of new cities pop up. I mean, I worked on multiple projects in China where you work on a concept plan of some farmland sometimes, and then within 2 or 3 years, an entire city appears from nowhere. So thinking about how those developments are done in a low carbon way is a lot of the focus of our work these days. So we've developed an approach for doing that. But the challenge is there isn't really a crystal clear answer. That it changes everywhere you go. And the reality is, here you are today trying to get to some point in the future, be that net zero or 1.5 degree stabilization or of temperature. But the journey to get there over a long period will actually not be a linear journey. You're going to go in different directions, and there's actually multiple pathways to get there. So one of the things that we do is try and develop robust plans for developments, organizations, whatever, that will get them there, but have enough flexibility to, if things change, like COVID, for instance. I mean, we've been working with another one of your peer universities, probably a slightly lower tier, to be fair. But they had pretty ambitious growth plans for the university, more or less doubling in campus size by 2050. But since COVID, they've rapidly backtracked on those growth projections, because their view, I don't particularly agree with it, is that more and more students are going to move to a permanent remote online learning. For lots of different reasons, I don't think that's going to be the case, because I think a massive part of education is actually the interaction and being on campus, which I'm sure you guys could tell me if that's the case or not. So that's part of our approach. And the second part of our approach in terms of low carbon development is we have this kind of step diagram in terms of how we actually get that, how we get there, starting with the baseline of where we're at, and then slowly chipping away at whatever energy or carbon emissions there are associated with the building or an infrastructure type. So generally that means reducing energy load first, in terms of using many passive systems, using the climate, using materials, etc., as in more insulation, orientating a building, etc., and thinking about load reduction. So that's basically how you use the building effectively, thinking about it in a more intelligent way, thinking about better active systems, so more efficient systems, such as heat pumps, then thinking about energy recovery. And only then do you start to get into renewables. And then once you can't bring it down any further, you get into carbon sequestration and offset. A lot of people think that low carbon planning is they jump straight to this bit, renewables and offsets. Those are the last resorts. The heavy lifting has to be done in terms of bringing your energy use down in the first place. And then we have a whole kind of, as an approach in place for doing this kind of project. And I'll tell you more about the university in a minute. Basically, we look at what are the goals, what is it you're trying to achieve, and then looking at a whole bunch of different technologies, looking at a bunch of metrics to screen which technologies would work, which ones wouldn't, and then bundling those together into different scenarios to try and meet the outcome that you're looking for. And then we basically develop a whole design to implement whichever there is preferred. But the other thing about low carbon planning for campuses, maybe that new development as well, is it's not really just a technical problem. A lot of people think it's just a technical problem, but it's also a lot to do with the stakeholders. So within a university, you have a lot of stakeholders. You have yourselves, the students, and faculty. You also have facilities managers. You have the people actually run the university from the administration perspective. You've got planning departments. You've got facilities, and then you've got the external community. So there's a lot of different stakeholders that are involved in the whole low carbon planning aspect. You need to really consult with everyone. And then the other aspect of it is, as I say, it's not just a technical option, because you can solve any problem technically, really. If you throw enough money at it, it's really working out the business model that goes along with that. How are you going to pay for it over time? What are the risks involved? Who else do you need to partner with to make it work? You're seeing within the university space, certainly you're seeing a lot of privatization of utilities just now. So universities are basically saying our core business is education. We don't want to be running the facilities on this campus. That's not our core function. Let's basically farm that out, and someone else can come and do that and just charge us for our utilities. And it's a way that universities can actually make money, because they sell all this for someone else to use. So there's a big movement for that in higher education just now. So now I'm going to skip gears to talk about the University of Toronto infrastructure planning work that we did, which is the sort of main focus of the presentation. So if anybody wants to ask questions, just to remind everyone, please stick your hand up or put something in the chat. So university came to us a couple of years ago and with three major challenges they had in terms of their infrastructure. So one is the infrastructure within, I'm talking mainly about the energy infrastructure, excuse me, is very old. It's an old university. It's with a fantastic campus and layout. Some of the buildings are well over 100 years old, as is some of the infrastructure. So it has been looked after, but it's just kind of past its sell-by date. And then the second challenge is the university is very successful and is growing quite rapidly. And there's lots of plans for it to continue to grow in the future. So how do they accommodate that new growth? And then thirdly was a commitment to reduce greenhouse gas emissions. So there were some commitments made to reduce by 37 by 2030. But then we worked with the university to develop some targets for 2050, which was basically a carbon neutrality target. And how do they achieve that, considering they've got some old infrastructure that's delivered just now in a not very efficient way? And then again, they're going to add to the campus by adding all these extra buildings, wobble up more energy. So we start the process by, from the very top strategic looking at what some of the commitments that have been made, what's Canada signed up to, what's the province signed up to, what's the state signed up to. There was a sort of seminal document that the City of Toronto wrote called Transform TO, which was its own kind of climate action plan and how it's going to deal with, or how it's going to reduce its emissions, etc., which was an 80 by 50 reduction. And then we start to look at what were other universities doing. And we looked at a bunch of North American universities just to see what kind of commitments they were making. And what you see on this axis here is that this was basically the amount of tons that they were producing of carbon equivalent emissions. And then what commitments they'd made by when. And the interesting thing is there's a different version of this diagram which shows that some of these commitments were made 10 years ago. Some very progressive universities, and basically every single one of them just blew right past their targets and did not achieve them. So a lot of the universities have now revised these targets, but we just want to see where University of Toronto fit in with the pack, so it could make an ambitious target as well, or develop an ambitious target as well. So it would be seen as continue to be seen as one of the premier universities and ambitious in its carbon goals, because that's important for students and faculty as well. And then we look at the climate as well. I mean, this talk is mainly focused on what we call decarbonization, so trying to reduce the impact of climate. There's this other factor which I'm sure you're learning about of adaptation or resilience to climate, as in how do you protect yourself from the climate as it's changing. So looking at the climate now, these are kind of rich stats, but when you look at it into the future, by 2050, what you are seeing is quite a change. Temperatures are going up, you're seeing more hot days, you're seeing less cold days, and you're seeing a lot more rainfall. I think this is, So that's quite a change. So it means if you're designing infrastructure, you've got to basically deal with increased temperatures, which means you might need more cooling, you might need more insulation, etc. You're getting more of them. You're getting fewer cold days. Excuse me, I'm just getting an interruption here. And then, which could be a good thing, but then you've got to design your buildings, if they're going to be built tomorrow, to deal with today's cold weather, even though it might be not as cold in the future. So that poses a challenge. And then you've got more rainfall that you have to deal with in the urban context. You have to move that away from buildings, reuse that, whatever you want to do with it. And some of these changes in temperature can cause all kinds of issues from extreme heat. That can be challenging for people to be in and around extreme heat. Power outages happen because everyone's trying to pull the energy off the grid at the same time. Extreme cold still does happen, and that can cause all kinds of challenges and cracked pipes, etc. And then you get flooding as well. We did some analysis here just in terms of what this would actually mean for the university, and basically, as I said, it would mean a reduced amount of heating load over time. It would also, it would significantly increase the cooling over time by 2050. So it's quite a big change that you have to design for in terms of your infrastructure. And the other thing that we look at as a kind of context setting thing is what does a grid look like? And this varies enormously wherever you go in the world. Quebec and Ontario have a relatively clean grid. Ontario has a lot of nuclear, it has some natural gas, a lot of hydro, and some other renewables on it. Quebec, I think, has a much bigger hydro component, so it's very clean. But then, if you're working in Virginia, for example, in the USA, then that's very much sort of 90% is fossil fuel based. So that factors into the kind of technologies that you choose. And then what the next stage of what we do is we start to pull in the data in terms of what's existing conditions, how much energy has been used, how much square footage is there, and we do some comparisons with other universities to see it forming. Despite the fact that the university has a lot of old infrastructure, it actually performs quite well compared to other universities, because there's been a lot of work in a very good facilities department who actually maintains. Then we start to look at the actual infrastructure that's in place. How's it being supplied? Most of it is centralized within the university and the same facilities team that I was mentioning. But there are still some buildings that are standalone and are not on the centralized systems. One of the challenges that that university has, which I mentioned before, is a lot of the buildings are very old, and some of them are landmark or historical, which poses an additional challenge. But generally speaking, older buildings are much less efficient. So you can see in the sort of post-war era is when so much of the building were developed on the site, and that was not a particularly good era of architecture and design. So those are not very efficient. This was just around for the kind of oil crisis time when people start to think about efficiency a little bit more. So this poses a challenge because a lot of these buildings are inefficient, they're saying, use a lot more energy than they should be. And then, as I mentioned, a lot of the infrastructure is very old. The steam system is, you can see from this is a picture that's on some of the infrastructure within the university, which basically shows us it's over 100 years old and still working. You know, most infrastructure, generally speaking, heating infrastructure is designed for a maximum of 25, 30 years life cycle. So the fact this is still in place 100 years later is a testament to it, but it's probably not as efficient as it could be. And that, as you can see, this is basically a schematic of all the infrastructure across the universities. There's pretty extensive infrastructure going under the streets all around the campus. So dealing with that infrastructure and upgrading it becomes very, very complex. But one of the reasons the university is very keen to focus on renewing its infrastructure is because bad things can happen if you have old infrastructure and it's not well looked after. And this was one of your peer group universities that basically had to close a bunch of buildings down because of one of their steam mains exploded. I mentioned earlier on there was some planned growth for the university, so it's some pretty significant plans are predicted by between now and 2050. A lot of that is based on growth plans rather than actual buildings that have been scheduled and designed, etc. But essentially, we're talking about an 80% increase in the campus over time, which is pretty significant. As I say, when you're trying to drive your carbon and energy use down, by adding all this extra growth, it's kind of going the wrong way, which poses a challenge. But not impossible because, as I mentioned before, it's well within our capabilities to design net zero and even net positive buildings now. It depends on the use type. Like a lab is a big energy hog, and that can be more challenging. But it can be done. It just needs to be thought about very carefully. So we did some load mapping across the site, and these are just heat maps to say this is where the heat map, the intense heat use would be, and this is the one on the right is where the intense cooling would be over time. And when you go to 2055, that increases a lot. So this is all extra energy you have to try and find, and this is just to basically, the darker the color in the heat maps shows a more intense use. So the darker colors are basically associated with some of the labs and some of the older buildings and some of the very, very dense areas. And this is the same thing with the electrical demand, which increases over time as well. So one of the things that we looked at is electrification. I'll come back to electrification later on. But it is a big theme just now in our world of low carbon planning for buildings. And one of the things that we did was just look at what would happen if we electrified the campus. I'll show you this in a couple of different ways, but this yellow line here represents the electrical load. So that's basically your plug load. And this blue line here represents cooling. So this is the electrical energy that's used for cooling the building. And then this red line here looks at basically how much, if you were to heat the buildings electrically, this is how much it would use. My point being that this is normally produced through gas heating. But if you also convert your heating to electric as well, you've got a massive difference in energy use over time. I don't actually have the diagram on this particular graph to show you the cumulative value of these three together, but it ends up being a big challenge because you have to really upgrade all your electrical infrastructure. So just zooming out for a second, so what I was presenting there was just some baseline information of all the things we like to look at to try and understand the problem, as it were. But now I'm actually going to get into what does a net zero carbon campus look like, and some of the brainstorming that we do to try and work out how we're actually going to get there. So one of the things we did was just draw picture scenarios in terms of what this could look like. So on the left here, the series of the bars shows how things are just now, and if we try to get towards some kind of improvement in our energy and carbon performance without going completely crazy and uprooting all our existing infrastructure. So we looked at the carbon emissions in terms of where they're coming from. So the grid electricity provides quite a lot of, about 30 to 40% of the existing energy on the site. And then natural gas provides the majority of the energy coming to the site. Then we could actually provide quite a bit through on-site solar. Because of the scale of the campus and there's so many roofs everywhere, we can actually provide quite a lot of PV. And then we could potentially use some off-site university land to develop some solar that they could also, through a virtual agreement, feed into the university campus. So this is what it could look like if we didn't rip up all the infrastructure and tried to be more sustainable in terms of our energy approach. The challenge here is we've still got tons of natural gas, which is as you know, a fossil fuel, which doesn't set us up for meeting our carbon goal in the future. And we looked at other scenarios where if we tried to increase our grid electricity and then bring in the thermal load through biomass, same thing with hydrogen, bring in the thermal load through hydrogen. We even looked at micronuclear. There is such a thing where you can make very small scale nuclear plants and put them in the middle of urban centers. No one's actually doing it yet, but theoretically the technology is there and in development. And then we also looked at, forget trying to do these technologies on site, what if we went all electric? Is that something that we could consider, keep maybe a little bit of natural gas for some critical needs, and then really max out on the on-site solar? So basically an all-electric scenario. As I mentioned, we looked at some other technologies. Biomass, we kind of discounted that just because biomass, there's a lot, it used to be conceived as a zero carbon fuel. People have changed their minds on that now because basically you're just taking the carbon out of the cycle for a very short term and then you're putting it back in again. There's all kinds of logistical hassles for a university. The scale of the St. George campus, it would be tons and tons of trucks going through every single day. Deep geothermal is something basically tapping into the Earth's core to get energy out. That just wasn't feasible in terms of what's under the ground, but also doing that kind of drilling in an urban context. Hydrogen fuel cells, this is something we think will come of age in the future. Hydrogen as a fuel is really increasing in terms of momentum. The research that's going on, for example, in some places you have extensive gas infrastructure. Why rip all that out? Why not put hydrogen in it? There's kinds of challenges with pressure, etc., but it can be done. And as I mentioned, micronuclear is something very much in development and theoretically is possible as well, but probably too risky to do in such an urban environment. So these are some of the kind of technologies we looked at and discounted. And then we basically focused on the electrification strategy and how would we do that over time? You can't just rip out all the infrastructure overnight. That would be ridiculously expensive. It would have to be a gradual change over time. So the concept was to basically phase out the natural gas infrastructure, which is feeding a steam system, which is a very inefficient way of delivering heat, and then phase in electrical energy as a backbone, and then that would have to provide the heating, cooling, and conventional electric. And as I mentioned before, have some on-site PV and some off-site PV to try and get us towards carbon neutrality. So we looked at how we would do that in terms of the technologies, and we came up with a short list of what we called enabling technologies. And the key ones were geothermal, which is different to the other geothermal that I mentioned. This is basically what we call a ground source heat pump, where you're in the summer months where you have too much heat building, you're rejecting that out of the building, and you're sticking it in the ground and using the ground as a battery. In winter, when you need that heat, you pull it out the ground and you dump any cold air in the winter months, and then you just keep on using that cycle. Very proven technology. And then another one that we looked at is sewage heat recovery. So when you have a shower, you use all this hot water, it goes straight down the drain into the sewage. So the sewage is actually got quite a high ambient temperature. There's all kinds of projects now. There's a very famous one in Vancouver called something Falls, I've forgotten the name, where they basically suck the heat back out of they have a kind of envelope around the pipes, and they suck the heat out of the sewage system, and that gets pumped through heat pumps back into a municipal heating system. And then we looked at air source heat pumps. Heat pumps are incredibly efficient technology where they basically convert outside air. You can have water ones, ground source ones, where you basically convert heat with electricity into a very efficient medium, and those are gaining huge popularity in the world, and the efficiencies are increasing all the time. And then we looked at electric boilers, which are 100% efficient, or very close to, so more efficient than a gas boiler. Very expensive to run because you're using electricity, which is an expensive fuel type in lieu of gas. But the advantage of electric boilers is you can keep all your existing infrastructure, your steam infrastructure, etc., and you just replace the natural gas boiler. You'd have a much bigger energy bill at the end of it, the limited capital expenditure, arguably. Then we looked at some other technologies to kind of augment those main technologies. Solar thermal, solar storage rather, basically giant tanks which could be underground or above ground to store heating and cooling for the periods that you actually need them. PVs, photovoltaics across the roofs, I already mentioned that. And then solar thermal, so like PVs, basically generating hot water through a panel. Oh, sorry, I forgot I had these slides which talk about a little bit more about some of these individual technologies. Ground source heat pumps was something that, long story short, the university is very much in favor of these. We're actively developing a project, and they already have an existing one to install these across the site. You can put them anywhere. This image here is someone actually in a underground parking garage retrofitting a ground source heat pump. Obviously, the best done before you do that, rather than retrofitting them. You can do them when you put the piles in for a building, for example. Air source heat pumps. These are also very popular, as I mentioned, very efficient. The challenge with these is they do take up a lot of space. You need a lot of roof area with these things because they're pretty giant for all the heat recovery units, etc. Sewage heat exchange, as I mentioned earlier on, basically sucking the heat out. The challenge we had with this is there's basically not a lot of main sewage pipes going through the campus, so it wouldn't make much of an impact in terms of the amount of energy that we need. And then, as I said, the electric steam boilers, they make sense in some ways because you don't have to rip out the infrastructure, but in other ways they're very cost prohibitive in terms of the use. So basically, we thought we could use these as backups when we needed them. And then I'm describing some really big macro scale interventions here, but the reality is the campus is incredibly diverse, as I was saying. lots of different building types, different use types, different ages of buildings. So it would be a much more nuanced kind of strategy when you come to actually retrofit all the different buildings. So this is just looking at what would happen if, actually getting into some numbers about if we did go all electric. So this is looking at our current situation. So this is our 1990 baseline in terms of carbon emissions. This is our emissions right now, well, from 2018, as close as we get, as a cogen, which produces heating and power at the campus. It uses up tons and tons of carbon. So this big red line here, this big red bar here is all the carbon emissions that it produces. And then this orange one here, or the little orange one here, is basically where buildings are not on that main network and they're doing their own gas. And then the other two are basically electricity that's consumed from the grid separately. So that's what it looks like now. If you got rid of the cogen, that would bring down your carbon emissions, and you'd have to replace them with low carbon electricals from the grid. If you got rid of all the natural gas boilers, went all electric, that would get your carbon emissions down even further. But as I mentioned before, the Ontario grid isn't completely free of carbon. There is still some carbon in there, so it doesn't quite get you below this line, which is our target for 2050 of 80% reduction. And then you'd basically, if you went all electric heat pumps, which are a mixture of ground source heat pumps and air source heat pumps, and we would actually be able to make our target. If we add on all the future growth that I was mentioning, this is what that looks like. So here's your 1990. Here's 2050 scenario, just continued business as usual. This is what would happen if you went with all electric boiler. It still would not quite meet your target. But if you went all out in the heat pumps using electricity because they're so efficient and lots of ground source heat pumps, etc., then you could still make the target. So that analysis kind of really focused our work and said, okay, we're going to go all electric and go for heat pumps in different shape and forms. I appreciate I'm throwing a lot of information at you here, so hopefully you're taking it in and you've got some good questions. As I mentioned before, one of the challenges with going all electric is we are basically hedging our bets on the grid. And the future of the grid is uncertain, and because there's so many things that are playing into it, and there's nuclear plants that are on it, etc., which at some point will come off, and they will have to be replaced by something. And the question is that going to be other renewables going to come on sufficiently quickly enough? They're going to basically replace whatever nuclear comes off, and it won't be replaced by natural gas or whatever other fossil fuel. And we don't really know that, but the best guesses say that it'll probably continue as it is for some time. It'll get better in some ways and worse in other ways, so it'll basically level off. But it is a challenge, and this is always a challenge when we're doing these projects in different parts of the world, is if we start to move towards electrification, which the world is doing in general, you have to have your grid kind of towing the same line, otherwise you're moving in the wrong direction. As I mentioned, right now in Virginia or someone like that, some of the southern states of the US, they're still using coal, and they have no policies in place to change that anytime soon. Then it would be more challenging to come up with an all electrification strategy. Having said that, market forces are kind of accelerating past regulation in some places because things like PV have become so cheap. When I first started working in North America 15 years ago or something, it was about $15 a watt installed for a solar panel. Now it's less than $1. So huge difference in that time. You're going to see the same changes happening with batteries, etc., as well. So all that analysis that I've been showing you basically fed into three main options. and this is where we are. I'm not going to show you exactly where we've ended up because it's a little bit sensitive, but some three main options we kind of ended up with. One is keeping the central plant and distributing low temperature hot water instead of steam throughout the campus. Basically, we'd have steam and then transition to low temperature hot water over time as you retrofitted all the buildings, and then you retrofitted the central plant. Then looking at having individual nodes, so not one big central plant, but different little plants across the site that would be supplemented, have steam in the short term, and at longer term they change to low temperature hot water. And then the other option was basically just a bunch of much smaller plants feeding 2 or 3 buildings at a time. With lots of air source heat pumps and stuff. But one of the main backbones of all these strategies is ground source heat pumps would basically feed into all of them. So these, as part of our work, we developed a kind of schematic of how all these different schemes would play out, where these things would be located, how big the ground source heat pump wells would be, or how deep they would be, and how many there would need to be, where the air source heat pumps would be, which buildings it could be integrated into. This is a central one that we developed. This is the nodal one, and this is the sort of more dispersed one. Don't go into the details of those. And then across these 3 different options, there were many others. We developed a whole evaluation framework to basically assess which ones perform the best based on some criteria that we worked out with the university. So these are the kind of headline categories: environmental, resiliency, operational, social, economic, and they had a sort of weighting to them. And there's a whole bunch of subcategories behind these, just to determine which one worked best for the university. As you can imagine, meeting the carbon goal was critical, but so was the operational cost and the capital cost involved. Doing massive retrofits is not cheap, so we had to look at it over a kind of 30-year life cycle to see how it was perform and whether it was basically going to pencil out against a business as usual scenario. It's the end of the University of Toronto. We're still kind of finalizing exact pieces of that. There's a whole implementation plan and tons of detail behind it. I'll just give a very high-level kind of overview. Just with the last few minutes, I'm just going to quickly show some other kinds of projects. So this is taking exactly the same concept, but to a completely different place. So this is a project doing in Cairo just now, working with a local architect based in Toronto. And this is a brand new development, greenfield site on the outskirts of Cairo, as I said, and looking at the energy strategy for that. How do you try and achieve the same sort of low carbon goal in a completely different context? And it's a very similar approach. The energy strategy was based on having the new design that makes it a lot easier. Having it highly efficient and highly insulated, as you can imagine, it's a very hot and mostly dry climate there, which actually makes it a lot easier to work with than the Toronto climate, because heating is not an issue, really. There's a tiny little bit of heating that's needed if you don't insulate your buildings, but if you insulate your buildings well, it's not an issue. And then going all electric for whatever cooling is needed. And then using PV, the PV resource in that part of the world is amazing. Right now, the grid there is very, very dirty. They have their own fossil fuels there, and they burn them to make lots of energy. They actually export energy, but they do have some aggressive goals to become more renewable in the future. So our strategy was basically hinged around that. Egypt has a long-term plan, as does Morocco, to be a massive solar region and actually export energy to Europe because they have such great solar resources there. So as I said, we went for an all electric strategy, and that meant all the heating cooling gets delivered through heat pumps. Cooking is through electric, which is pretty controversial. We'll come back to that. And then even your hot water is delivered through grid electricity. Hot water too. As I said, it's funny when you work in different places, you have different cultural phenomena that kind of have to factor into your design strategies. One of the things that we recommended is going all electric on everything, and that there's a cultural, as there is here as well. People like cooking with gas; they don't like electric. But we've had to do some convincing with the client that induction cooling is actually induction cooking is actually a much more efficient way of cooking, and it's not like the old electric cooking that you used to do. So we've persuaded the client that that's actually something that's worthwhile. I'll skip through this just in the interest of time, but this was some of the analysis that we did in terms of the loads. But one of the questions that we had to answer is, what if you went fully electric as opposed to using natural gas, etc., for any heating and hot water and cooking? Does it make a big impact? And the reality is, it really doesn't. It increases your overall electrical load by 4% here, and your average energy consumption by 7%. If that was Toronto or even New York, these numbers would look massively different because you'd be providing only heating with electricity, which would be a big challenge. But the other aspect is it does, obviously, by going all electric, it does increase costs. Gas generally across the world is much cheaper. So basically, for every thermal unit that you're consuming, you're paying double in terms of going electric as opposed to natural gas, which again is a whole kind of education that we had to do with the client. It doesn't actually impact. I mean, it doubles their electricity bill, but the electricity bills are quite low, and particularly if we went for all solar. So if we got 25% of the roof space to be solar, we could generate around 3 megawatts of electricity, which would essentially deliver about 23% of the energy load across the entire site, which is phenomenal. Most developments you get like 5%. If you're doing it in Toronto, covered similar development with PV, you'd get about 5% here because the solar resource is so good. Because of its location and because there's not a lot of humidity in the air, it makes a huge difference. And if you added battery storage to that, you could increase that even further. I think I'll leave it there actually, because I'm conscious that I've been talking for a long time and not had any questions so far, although I think one might have popped up. So maybe I'll pause there and I'll open it up to questions. Jamie, I don't know if people can actually talk, or it's just by the chat.
Let people talk just in case, because this is a fully public event, and you don't need a Zoom bomb or whatever they're called. But yeah, so if anyone has questions, just to put them in that chat. So you at the bottom right hand corner of your screen should see a little purple arrows there, and then you click it, and the chat bubble on the left side. You should be able to type in there what you want to ask. We do have one question from Jim number 2, and Jim is asking, with the world warming, cooling will become increasingly important. Are there technology breakthroughs required to improve cooling, or are current technologies sufficient?
The short answer is no, that current technologies can be massively improved. I mean, one of the challenges with heat pumps that I was mentioning before is they still use refrigerants, which have their own carbon challenges in terms of how they're developing. But there's a lot of technology in development using water as a coolant in the heat pumps, but also CO2 itself and other things. So they can always be improvements, but heat pumps have improved significantly over the last sort of decade or so. It used to be that people would always, well, people still do, they always say, oh, you can't use a heat pump when you go this far north because it's too cold in the winter. But now heat pumps have really improved to be able to really operate in a much bigger range and go to able to provide heating at much lower temperatures. There's still challenges. I mean, if you go really far north, then they'd really struggle. So there's still a lot of improvements to be made there. Second question, embodied carbon, was that taken into account in the U of T analysis? No, it was not. That's something, another level of detail I think we'd like to go to in the future. Speaking generally as a sustainability practitioner, the embodied carbon, we're just at the cusp of people starting to understand or starting to appreciate the importance of it. I mean, some of the analysis we did a few years ago is if you get a net zero building, and obviously its carbon emissions are zero or very close to zero, all the carbon's in the building. So why is no one doing anything about that? So within Europe, you're starting to see a lot more regulation now creep in. You have to provide carbon analysis when you develop a new building, for example, in certain regions there or certain states. So I think we're going to see much more of that, but it wasn't taken into account for this analysis. Next one, was the consideration given to using the deep water cooling via N-wave? We did consider it. It's complicated. I won't get into the logistics of the N-wave too much, but one of the challenges, for example, we tried to develop our own deep water cooling. We're too far from the lake. There's all kind of challenges with, someone like University of Toronto doing it themselves. The N-wave system right now is tapped out. It's at capacity, and they're trying to bring in additional pipelines to basically extend it. But we didn't want to basically rely on that in the future. Can you mute yourself, Jamie? I think you have done, Jamie. Can you expand a bit on the impact of the geothermal projects on the campus? Approximately what percentage of total energy demand can be supplied by the projects in the front campus and the playing fields on the west of the campus? Is the intention to expand this technology to other areas where there is open space? Generally speaking, I don't have the details at hand in terms of specific locations, but we did a whole lot of analysis across the campus looking at specific locations where there was open space that was obviously sensitive, or where there were going to be new buildings put in, and we could put them underneath those buildings, or buildings that might potentially be taken down, and we could put them in there as well as new buildings. So there was quite a detailed analysis that was done, and there's a couple of pilot projects, which I'm not sure if I'm allowed to talk about them just now, so I'm going to say no, and I can get back to you. And there's another question from Sherry Ann there, asking, I think, a pretty similar question. I mean, what I am talking about is Sherry Ann, is a traditional geothermal heating system. We're just talking about developing some quite large fields of it, so not just for a single building. It might serve multiple buildings, and they would also be connected to each other, provide heating and cooling to multiple buildings at the same time. And it would also, in some cases, it would be more of a kind of condensing loop where buildings can swap energy in real time between each other. So, a lab that's rejecting heat all the time could potentially be used by a residential dormitory building just beside it, which again has been done across the world. So another question from Alex there. How does ARUP consider behavioral social changes, e.g. energy conservation or reduced demand for future emission projections? Or is it focused purely on technological solutions to reduce GHGs? We do consider that. It can be quite a dangerous game if you rely on it too heavily. And engineers, being engineers, like to be conservative with our thinking when it comes to this stuff, because there's been plenty of studies to say that when you put, for example, dashboards in within a building, so people can see their real-time energy use and understand their habits, that their behavior does change in the short term, but then they often slip back into their bad habits, or they plug something else in because they think they're saving energy in another way. So it can be quite challenging. I mean, one of the projects that we did for a different university in New York, which was the Bloomberg Center on Roosevelt Island, which is a net zero building. One of the challenges we had there was we really brought down the energy loads in terms of heating, cooling, etc. But one of the challenges was that university students now all have their own laptops, they all have their own mobile devices, etc. And they're all plugging that stuff in. And you can't stop them doing that because by code you have to provide a certain amount of outlets in certain spaces. So that was something we couldn't really control, and it's also something that's always changing as we become sort of more reliant on digital devices. Those loads are actually kind of going up over time. These are all excellent questions and stuff we need to consider. I mean, one of the slides I had at the end actually, in terms of sort of future considerations, was in terms of doing this work, I kind of glossed over the fact that energy retrofits is a huge part of this. Incredibly expensive. It's actually sometimes more expensive to retrofit a building than it is to build a new one. That all needs to be done. So when you change the steam system for a building, as in the delivery system, you also have to ripple the steam system out within the building is arriving at, which can be expensive to do, can be done again, but there needs a whole business model to go with that. And then the infrastructure needs to be changed. But the other things that are, moving targets, as it were, is grid makeup. If the whole world goes electrified, that has massive implications for grid. I didn't show the analysis there, which sort of summarized how much our electrical loads are going to go up by, but that all has an impact on the wires that are needed, but also the energy that's supplied through the grid, where was all going to come from, etc. And then the other things are things like electric vehicles. If everyone starts plugging their electric vehicles in everywhere, and that's not regulated, which it can be, that can pose a challenge. Not so much for the University of Toronto because there's very limited parking. But on the positive side, there's things like carbon taxes, which are going to come in and make all of this more attractive to do going forward in the future. Other question on COVID. So how's that impacting planning for U of T campus? I can't really answer the question in terms of what the U of T is thinking lately in terms of COVID impacts. In terms of future growth predictions, as I said, another Canadian university I've been working with has really ramped theirs down. In terms of indoor air quality considerations, it does have an impact. It's actually leading to inefficiencies right now because people are using their existing systems and they basically have more air exchanges, which means that all the HVAC systems are having to work harder. And if there's no heat recovery in there, etc., then there's a real penalty to do with that. And it's going to be, in the other world that I work in, commercial real estate, it's really going to be very interesting because when people do start going back to work wholesale, are people going to go back in the same numbers they used to? Therefore, there's going to be more commercial real estate potentially sitting empty. At the same time, they're all going to have to upgrade their commercial rate to make it a more comfortable place and healthy place for people to want to come to. So they're going to get hit from both sides. You use machine learning to for your modeling outcomes. Yes, that is something. I didn't get into it in this one. We didn't actually use it in this project, but it's something we're using a lot more of, particularly with some of the work we do at a bigger scale. Again, basically we're doing the climate action plan for the state of New York and the Commonwealth of Massachusetts, which means we're looking at all the different aspects of energy and carbon within the states. And that way we're looking at different kinds of buildings, and there's like 30 different kinds of buildings. tons of different ECMs you can look at. So we're using machine learning there to run thousands and thousands of iterations at the same time, learn from those iterations, and then move on to the next iteration, etc. Stuff that we couldn't have done a few years ago. And it's really made our whole modeling process much more efficient. So I think we're going to be seeing a lot more of that in our industry going forward, as you know, we'll be able to come up with more intelligent solutions. Right now, a lot of mechanical design is done through intuition, backed up by analysis, rather than a lot of the machine learning that could be used to inform that to a better degree. Is there a way to meet the U of T carbon goals if the Toronto grid were to start switching back to natural gas? We'd have to generate more power on site through one of the alternative uses. I think we'd have to go with hydrogen or something like that. If the grid started turning electric, I mean, there's not enough solar space on the campus to basically generate our own electricity there, so we'd have to come up with some other way of doing it through, as I say, hydrogen or nuclear or even biomass. But that has huge challenges. I think we're out of questions. Over to you, Jamie.
Yeah. Well, thank you, Cameron, for giving this really great presentation. And I think I don't think we had anybody actually leave the meeting during the presentation, and that's a good sign. And,
Thank you.
Really good and thoughtful questions too. So I think this went really well. And so I'd like to thank you for presenting on behalf of the CSE and the University of Toronto. And I'd like to thank everybody who came to attend. It's always great to see everybody come out. And I think that pretty much wraps it up. So thanks everybody for coming. If you're a U of T grad student, don't forget about those workshops that are being promoted right now. And other than that, I think that's it. So just have yourself a nice evening.